how are you? I know you are enjoying my videos. Now let's enjoy today the new topic, atmospheric refraction. Okay, as you know, what is the atmosphere? Atmosphere is it is just like the blanket of the different gases around the earth. So there are so many gases around the earth. So when the rays passes through these particles, because in the atmosphere there are so many particles like the dust particle, water droplets, etc. There are so many particles. So when the light passes through it refracts, because air is almost the transparent medium. So refraction through the atmosphere is known as the atmospheric refraction. It's very easy to understand what is the refraction. Now today we'll discuss the another topic, that is the example of the atmospheric refraction. First example we can take, that is the twinkling of the stars. Okay, so twinkling of the stars, sometimes twinkling means when you see the stars in the sky, you can see sometimes the intensity of the light which is reaching in your eyes becomes low, and sometimes it becomes very high. That is, sometimes it is very dim and sometimes it is very bright. So this is known as the twinkling of the star. So what happens in the twinkling of the star? Actually, suppose this is the sun or the star. Suppose this is the star, okay, and you are standing here, okay, at the surface of the earth. So these rays should reach like this in your eyes. But since there are so many layers of the air, and you know the density of the air always decreases when we go in upward direction from the earth's surface, in up direction. So the density always decreases. So the layer which is at the uppermost, that is the near the star, it's of less density. So density is increasing. Here you can say the density, it is increasing when you go downward direction. So when the sun rays, or you can say the star rays reaching your eyes, it is passing through the different layers of the different densities. And you know, when the ray comes from denser to rarer medium, in that case this ray always bend away from the normal, away from the normal. So similarly here, the sun rays or the star rays or the starlight, when it is coming downward direction, it is coming from rarer to denser, because it is the rarest, okay, and it is the density is increasing. So it is coming from rarer to denser, and in coming from rarer to denser, suppose it is the rarer, so in denser it will bend towards the normal. So these rays will continuous bending towards the normal, and when you see the star, it is not exactly at the actual position. You see it's at different position, which is known as the apparent position of the star. It is something different. It is always something different, and little higher also from the earth's surface. It is due to the change in the density of the different layers. Okay, so twinkling means actually the air which is just near the star, it is continuously changes. That is the layer of the air is continuously changes, and its density is also continuously changing. So the light which is reaching in your eyes, it is sometimes like this, it is refracted, bent towards the normal, and sometimes it is bent away from the normal. So the intensity of the light which is reaching in your eyes, it is always different. Every moment it is changing. Sometimes it is in this direction, and sometimes it is in this direction. So that's why always you see the intensity or the intensity or the brightness of the light coming from the star is always different, and this term is used, that is it is the twinkling. So star is twinkling only due to the change in the density in the atmospheric layers of the air, and the light sometimes it becomes very dim and sometimes it is very bright. Now question arises when you see the twinkling of the star, why the planets do not twinkle? Why the planets do not twinkle? You can understand the twinkling, not twinkling of the planet. Actually planet is the, you can imagine the planet, it is the bunch of the so many stars, and it is very near to the earth. It is very near to the earth. So that is the refraction, sometime bent towards or the away from the normal, it becomes very low, very less, and because it is the bunch of the star, suppose the light coming from the one star is some at a moment it becomes dim or the less, so at the same time the light coming from the other point, that is the other star, it is becomes more. So average intensity of the light which is coming from a planet is always constant. Okay, suppose the there are 10 stars or 10 source of the light, so 5 becomes low intensity and 5 becomes less. Okay, so in that case what will happen? The average is always same, that is the, you will not see the variation in the intensity of the light which is coming from the planets. So that's why the planets do not twinkle. This is the exact reason why these are not twinkling or does not show any twinkling effect. Okay, now another example of the atmospheric refraction we can see, it is the advanced sunrise and delayed sunset. Means you see the rising of the sun 2 minutes before, and you can see the sun after setting 2 minutes more. Okay, means you can see 2 minutes early and 2 minutes later. Okay, so there are only it means there is 4 minutes difference. It means the day is increased by 4 minutes due to the atmospheric refraction. Actually what happens in this case, suppose this is the earth, see, try to understand, this is the sun and this is the atmosphere, you can say. Okay, and so suppose observer is at some place here. You suppose this is the horizon. So horizon, this, when the sun is coming, rising, so it is just below the horizon. Suppose this is the sun, it is below the horizon and it is coming above the horizon. So before 2 minutes, it is refracted in such a way. That you can see here early, 2 minutes early. And suppose in the same way, when it is setting, in the same way you can see 2 minutes more also. So there is 4 minutes difference. It means due to the atmospheric refraction, the length of the day is increased by 4 minutes. Remember, it is the 4 minutes. Okay, now see the another phenomena, very interesting phenomena, which is known as the scattering of the light. See what is the scattering of the light? Scattering of a very natural phenomena. We can see the examples of the scattering of light around us. It is very common phenomena. Actually what happens, so when the light incident on a particle, atmospheric particle obviously, so First is it absorbs all the light. Suppose this is the light ray, so it is absorbed by the particles present in the atmosphere, and then this light is spread in all directions, like this. Suppose this is spreading like this in all directions, so this spreading of the light, first absorb and then spread in all possible directions, is called the scattering of light. So Rayleigh was the scientist who told about the amount of the intensity of the light due to the scattering. According to him, the scattering, that is the intensity of the scattering, depends on the wavelength of the incident light. So according to him, the intensity of scattered light is always directly inversely proportional to the fourth power of the wavelength incident on the particle. It means more wavelength. If the wavelength is more of the incident light, then the intensity of the scattered light will be very less. So this is the reason why the red color, whose wavelength is maximum, it is scattered very less. So least scattering shown by the red color always. And the another minimum scattering in the case of the VIBGYOR, it is the violet color. So red is scattered least and the violet color, it is scattered maximum. So on the basis of this, we can understand some more phenomena, but before that, see another effect, and then we'll discuss its example of the scattered light. Now another one more example, it is also the scattering, about the scattering, special type of scattering, that is it is known as the Tyndall effect. Okay, so what is the Tyndall effect? It's same reason. You can see, you know very well, there are so many particles in the atmosphere, so many particles. Okay, and different type of particles, dust particle, gas particles, water droplets, etc. So when light incident or passes through it, the path is illuminated. So this illuminated path is termed as the Tyndall effect of the light. So Tyndall effect, you can see the example in our daily life also. Suppose you entered in a room which is dark, that is, no light is inside, and some small narrow beam of the light is coming from the window or some hole entering into the room. In that case, you can see the visible dust particles like this, visible. So this visible path is shown by the light, and this is due to the Tyndall effect. If the size of the particle is very less, in that case you will find the after scattering red, that is a violet color. It scattered maximum violet color if the particle size is very small, tiny particles. Okay, and if the particles are large, in that case it will scatter the red color. And suppose the light is that is, the particles are much large, in that case scattering will be no scattering will be there, and it means the all colors will be reflected, and you will see the reflected light as a white light. So this is about the Tyndall effect. Now on the basis of the scattering of light, we can discuss why the sky is blue. Okay, why the sky is blue. Okay, see what is the reason behind the bluish sky. Actually, what happens, according to this rule, the if you see the VIBGYOR like this, VIBGYOR, okay, so this effect is the reddish effect, and this effect is the bluish effect. Okay, it is the bluish effect, and this is the reddish effect. Okay, this is the reddish effect. So what happens, because the wavelength, it is the portion where the wavelength is more, and this is the portion where the wavelength is less. So when the light, that is the sunlight, that is the white light, passing through the atmosphere, so the red color will scatter minimum. So which color will scatter more? That is the bluish. Okay, because its wavelength is very less. So blue color or bluish effect you will see in the sky. That's why you see the sky or the atmosphere around us blue. Okay, this is the reason why the sky appears always blue. Okay, if there is no scattering, just imagine if there is no scattering, or is there imagine a planet where the no atmosphere is present. In that case, due to no scattering of the light, there will be dark. That is the no color you will find. Okay, this is the reason why astronaut, when go above the gravitational field of the earth, above the atmosphere, he can't see the any color, and the sky above the atmosphere is always black. This is the reason. Okay, see another example of the scattering, that is the color of the sun. Color of sun at sunrise and sunset. Okay, so at the time of sunrise and sunset, we see the sun always red. We see always red. What is the reason why we see the red? Actually, what happens, suppose this is the horizon. Okay, and sun is rising. Sun is suppose rising, or this is the horizon, this is the earth, and sun is suppose rising or the setting. So at that time, the distance of the sun is maximum. So, and you know, according to this rule, the red color will scatter least, because its wavelength is maximum, so it will least scattered. So this least scattered color will reach in your eyes. You are here, so these colors, that is the red color, will reach in your eyes, and you will see the sun red. Okay, because rest colors, that is the bluish color, it will refracted, it will scatter in the sky, and sky becomes blue. But the sun will appear always red due to the least scattering of the red color. And the same thing you can apply about when the sun is setting. So in rising time or setting time, when the sun is at the horizon, it is at the maximum distance. Okay, and see the another example at noon time. At the noon time, the sun is at very less distance. This distance, noon time, that is around 12 o'clock noon, its distance is minimum. So all colors are reaching in your eyes, and presence of the all color, you know very well, it is the white. So that's why at the noon time, sun appears white. This is the reason. So reddish appearance of the sun, or whitish appearance of the sun, it is due to the scattering of the light. So this is all about the scattering of the light, and I hope this session of the physics is very interesting. You are trying to understand everything. In next video we'll discuss its exercise questions. Thanks